Hello and welcome back to the Deep Dive. Today we are taking a trip down memory lane, or maybe for you, it's just a trip to yesterday morning.
That's probably more accurate for a listener.
Exactly. I want you to close your eyes for just a second. Imagine you're back in the school chemistry lab. You know that specific smell? A mix of rotten eggs.
Hydrogen sulfide. And that dusty smell of old wooden tables. It's a sensory memory that never, ever leaves you.
It really doesn't. And somewhere in that room, maybe peeling a bit at the corners, is that massive, colorful chart, the periodic table.
The one we all stare at during practicals, trying to remember a molar mass.
Yes. But have you ever really looked at its shape?
It is quite a peculiar piece of architecture, isn't it? It's certainly not a perfect rectangle.
No, it's not. And that used to bother me so much. You have these two tall towers on the left, groups 1 and 2. Then suddenly there's this long, low valley in the middle. Then it rises up again on the right. It looks broken.
Like a castle where the middle wall collapsed. I've heard that one before.
And then, to make it even more confusing, you have those two long rows floating completely separately at the bottom, like they were exiled.
That's a very vivid and actually a very accurate description. And for a Class 12 student, that weird shape is the most important clue in the syllabus.
And that is our mission for today. We're doing a deep dive into Unit 4, the DNF block elements. But we're not just memorizing trends. We are answering the question, why does the map look like that?
Why does that bulge exist? And why are those two rows in the basement? It's crucial because in chemistry, position is everything.
Position determines destination. That's what you said in the pre-show notes. It sounds a bit philosophical.
It does, but it's practically true. If you know exactly where an element sits, you know its electron configuration. And if you know its configuration,
You own its chemistry.
you own its chemistry. You know how it bonds, if it's magnetic, if it forms colored ions. If you don't know the address, you're completely lost.
So consider this deep dive your GPS for that messy middle section. Let's start at ground zero. How do we define the D block simply?
At the absolute simplest level, just think of the D block as the filling in a sandwich.
Okay, a sandwich. So the S block is one slice of bread on the left, groups 1 and 2.
Correct, the highly reactive metals. And on the far right, you have the P block, groups 13 to 18. That's your other slice of bread.
And the D block is everything squeezed in between.
Everything caught in the squeeze. Specifically, this happens across 3 main rows, periods 4, 5, and 6.
Right. And the F block, where do they fit in this sandwich?
Well, they're not even in the sandwich. They're like the plate the sandwich is sitting on. They sit outside or below the main table.
You know, I was thinking about a better visualization, something 3D. Imagine the periodic table as a large building.
An apartment complex, maybe. Let's build it.
Okay, so the S block on the left, that's the entrance lobby. The ground floor, simple, accessible, just 2 apartments wide.
Accents.
The P block on the right is the main residential tower. Higher up, lots of tenants. But the D block. The D block is like discovering a hidden wing. A mezzanine floor tucked between the ground floor and the upper levels.
That's a great model.
Yeah.
And it's important to know you don't see this wing on the first 3 floors. It only opens up when you get to period 4.
Right. Floors 1, 2, 3, nothing. Then on the 4th floor, bam, this massive corridor opens up in the middle. That's the D block.
And following that logic, the F block has to be the basement.
The deep basement. Like the parking levels, maybe.
Yes, it's so hidden that on the blueprints, our printed periodic tables, they usually just put it on a separate page at the bottom.
Because if they drew it where it actually belongs, the blueprint would be too wide to hold.
Exactly. It would ruin the layout of the entire building plan.
Okay, so hidden wing and basement, I get it. But let's talk mechanics. Why? Why does this hidden wing suddenly appear on the 4th floor? What's happening inside the atoms?
Okay, so for this, we have to just recall a little bit from Class 11.
Uh-oh. Class 11 concepts. I can feel the listener panicking already.
Don't worry, we'll keep it very simple. It comes down to where the electrons are going. In the D block, they're filling the N1d orbitals, while the N's orbitals are already full.
Okay, pause. Pause right there. N-1d. That notation is exactly what makes students close their textbooks.
I know, it sounds like a math equation. It's much simpler than it looks.
Yeah.
N is just the outer shell number, the period you're in. So for period 4, N is 4.
Okay, so I'm on the 4th floor of the building. My outer shell is 4.
Right. And you've already filled the 4's orbital, so the outer wall of the 4th floor is built. But now, nature does something weird. Instead of adding more rooms on the 4th floor,
It goes back.
it goes back a step. It goes down to the 3rd floor at the N1 level and starts filling the 3rd orbitals.
Wait, so I've built the outer wall of the 4th floor, but now I'm going back inside to finish furnishing rooms on the 3rd floor.
That is a wonderful way to put it. You are filling the penultimate shell, the second to last one.
It's like retrofitting the building from the inside.
Okay.
And for the F block.
It gets even deeper. They fill the N2F orbitals.
So third from the last shell, the anti-penultimate.
Exactly. So if you're in period 6, you're not filling the 6th floor or the 5th floor. You're going all the way back down to the 4th floor to pack electrons in the 4 orbitals.
2 levels deep, hence the basement analogy.
Precisely. This inner filling is the key. It explains everything. Shielding effect, lanthanoid contraction, all those heavy topics. It starts here.
All right. We need an exam-safe definition. If the question asks, define a D-block element, what's the anchor definition?
This is the one to write down. The insert safe definition is, the D block consists of elements in which the last electron enters a d orbital. They occupy groups 3 to 12 of the periodic table.
Groups 3 to 12, the magic range.
Yes. And I have to point out a common misunderstanding here. A trap students fall into.
Ooh, let's fix a trap. What is it?
It's about the very first element, scandium. C students often ask, is scandium actually a transition element?
Why would they doubt it? It's right there at the start.
Because it's the first one. They think, well, it only has one d electron, maybe doesn't count yet. But the answer is a definite yes.
So scandium is in the club, no question.
Absolutely. Its configuration is 3dd4 The last electron went into a d orbital. It has a partially filled d orbital. It is 100% D-block transition element.
Good to know. Don't get confused on that one.
Correct.
Now, I want to try another analogy. This one explains the width of the table.
The horizontal expansion, yes.
Right. So imagine the periodic table is a concert hall.
A concert hall. Okay, I'm listening.
The S block, groups 1 and 2, those are your VIP front rows. Very exclusive.
Right next to the stage. Very energetic. I like that.
Naturally. Then you have the P block, groups 13 to 18. That's general admission in the back. But the concert organizer sold too many tickets.
Ah, so they need more seats for the transition people.
Exactly. So what do? They insert extra rows right in the middle between the VIPs and the general seats.
And how many seats do they add per row?
Exactly 10 for groups 3 through 12.
Which fits perfectly with the number of D-block elements in a period.
And the F block.
That has to be the orchestra pit. Below the main stage. Spatially separate, but definitely part of the show.
I like that because it explains the horizontal expansion so well.
And it brings us to the why. Why did nature need to shove those 10 extra seats in? Why not 8 or 12?
Yeah, why is 10 the magic number?
It comes down to quantum mechanics. A d subshell has 5 orbitals. Each orbital can hold 2 electrons.
So 5 times 2 is 10.
It has to be 10. Nature requires 10 spaces. Mendeleev just left gaps in his table because he knew something was missing. Modern chemistry tells us why the gap is exactly 10 columns wide.
It's unavoidable geometry. And for the F block?
F orbitals have 7 suborbitals. So 7 times 2 is 14.
14 columns. That's why the F block rows have 14 elements each.
You cannot argue with the math. The table is just a map of the map.
Okay, one more visualization. A mental movie moment. Picture a spiral staircase.
Okay.
You're climbing up, and each step is an element. Hydrogen, helium. It's a narrow spiral at first.
Just the S and P blocks. Very narrow.
Then you hit row 4. Suddenly, the staircase landing widens. It bulges out. You have to walk 10 extra steps across this landing, the D block, before it narrows again.
The transition series landing.
Exactly. And when you get to row 6, it gets even crazier. There's a huge hidden platform underneath the main stairs with 14 extra spaces on it.
That's the F block. The visual takeaway is so important here. The D and F blocks aren't mistakes. They are the natural widening of the staircase when new orbitals open up.
It makes the bulge on the wall chart seem intentional, not weird.
And if you go up to that chart in your lab, count the columns. You'll count exactly 10. It's so satisfying.
Speaking of charts, here's a tech example. We all use those periodic table apps on our phones, no?
Yes, very common.
Have you ever noticed that you have to scroll horizontally to see the whole thing, or the table looks all squished?
Yes. A classic user interface challenge.
Caused by chemistry? The D block makes the table too wide for a normal phone screen.
It does. An 18 group-wide table is very awkward for a portrait screen.
And this is actually why the F block is at the bottom, right? It's a design hack.
Basically, yes. Imagine if we put the F block where it technically belongs. The table would be 32 columns wide.
A long, skinny ribbon. You could never print it on a page.
Exactly. Separating the F block is a design choice to keep the user interface of chemistry usable and clean.
Okay, I have a question. Why not just list elements 1 to 118 in a straight line? Why all this trouble with groups and blocks?
Ah, the list versus table debate. A list might seem easier, but the table groups elements by chemical family.
Like a family tree.
Exactly.
Mm-hmm.
Copper is in group 11. Right above it is silver, and above that is gold. The coinage metals. They share properties.
And a straight list would lose all that context.
Completely. You wouldn't see that copper is the cousin of gold. The table is organized by where electrons fill, and that reveals the chemical soul of the element.
It's a chemical soul. That's deep. Okay, let's get down to business. The exams. Our listener needs the key takeaways.
Right, let's list the clarity lines. Get your notebook ready.
Okay, clarity line number 1.
It's about location. You must write. The D block occupies periods 4, 5, and 6, spanning from group 3 to group 12.
And why is that specific phrasing important?
Because it confirms there are 30 D block elements in the main body. 3 periods times 10 groups. The boundaries are key.
Got it. Second key point.
About the F block. You're right. The F block consists of 14 elements per row, occupying 2 rows. Lanthanoids in period 6 and actinoids in period 7.
And the common mistake here?
Forgetting they belong to periods 6 and 7, they are in some other dimension called the bottom. Cerium is in period 6. That's a classic trap.
Okay, third point, the definition.
Yes, an element is D block if the last electron enters a D orbital. Simple. Clean.
And it settles all arguments, like for scandium.
Exactly. Last electron went to third. End of discussion.
And finally, the fourth point. This one is a bit tricky, the name transition metals.
A very popular question. Transition metals are defined as B block elements with partially filled D orbitals.
Partially filled. Okay, so what about zinc? It's at the end of the D block, group 12.
You've hit on the key exception. Zinc is 3D air degrees. Its D orbital is completely full. So strictly speaking, zinc, cadmium, and mercury are not typical transition metals.
But they are in the D block.
Yes, they are D block elements. But because their D orbitals are full, they don't show the typical properties like variable oxidation states.
So is zinc a transition metal? The answer is technically no, but it is a D block element.
You have got it. That distinction can be the difference between a top score and a perfect score.
Fantastic. Let's do a quick recap before we sign off.
Let's do it.
So, core idea. The D block is the hidden wing squeezed between the S and P blocks.
Because of the L1D dollar filling rule?
Correct. The analogy. Think of the concert hall. We added 10 extra seats in the middle.
And the F block is the 14-seat orchestra pit below.
The reality. The bulge on your lab wall chart is physical proof of quantum mechanics.
And finally, the key clarity. Remember groups 3 to 12. Remember periods 4, 5, and 6. That's your map.
If you can remember that, you're set. To our listener, you have the map now. Position determines destination. You know where these elements live.
And now you're ready to learn how they behave. The fun is just beginning.
Before we go, leave us with one final thought. A brainworm for the day.
Well, we talked about how the D block adds 10 groups and the F block adds 14.
Right. The staircase just keeps getting wider.
Imagine. What would the table look like if we discovered elements that fill the next orbital? A G block.
A G block? Does that even exist?
Theoretically, yes. The math suggests a G orbital would hold 18 electrons.
Whoa, 18.
So, if we ever reach that island of stability, the periodic table would need to widen by another 18 columns. Where would we even put them?
We're going to need a bigger lab, a much bigger wall chart.
Indeed. That is something to ponder. The map might not be finished yet.
A G block. That's an amazing thought. Thank you so much for that insight. And thank you to our listener for joining us on this deep dive. Keep curious, and we'll see you next time.
Goodbye, and happy studying.